Today, Oliver will open this 3-part lecture series with the moduli space of matrix.
Thank you for giving this opportunity to present part of my work in these 3 lectures. And today I decided to go for slides to give you the full theoretical experience. But yeah, it's a story that I couldn't do on a blackboard like this. It's 2 slides, and you're welcome to ask questions. So you're meant to ask questions and slow me down where you don't understand things. So let me start with a little prologue and introduce the 4 main actors of the story. So I learned from Matroids, the master of storytelling, that you can magically wave your hands and move around blackboard and writing. So I got this little trick. So these are our 4 protagonists. So the first one is some guy that we know and love. The field has 2 elements. It has 2 elements, 0, 1. The multiplicative structure is the obvious one. And then the addition is captured by this addition table. 0 at 0 to 0. I mean, 0 is a neutral element. And the only interesting thing is that 1 plus 1 is 0 from the perspectives that I'm taking. The second guy is the so-called Krasner hyperfield. And it has the same set and same multiplicative structure. But the surprising thing is, well, 0 is a neutral element, but 1 plus 1 is now multivalent, can be 0 or 1.
So
0 plus 1.
Oh, yes. So addition is multivalued. For hyperfields, we don't define that, but the addition of 2 elements is a subset. So here 1 plus 1 would be the full subset. Our third protagonist is a so-called sign hyperfield, which has now 3 elements, 0, plus 1, and minus 1. You should think of this as positive and negative. And you add up 0 is again neutral, and you add positive and positive according to your expectation of the outcome. So positive plus positive is positive, negative plus negative is negative, but positive plus negative could be anything, right? And the last one is the so-called regular partial field. And this should be thought as a substructure of the integers. We can only add elements if the outcome is in the ground set. So, sorry, once again, the multiplicative structure is the obvious one. But then you can add 1 plus minus 1 and it's 0. But you cannot add 1 plus 1 because 2 is not in the field of definition. So in a moment, I will tell you a framework which captures all of these objects, but for now, just keep them as intuitive objects in your mind. Yes?
So the dash is like empty set?
Yeah, that's an empty set. Okay. So let me give you an outline of the talk, how it goes. So what I want to do in this talk, which was my, I don't know, first or second collaboration with Matt, but this started the whole story, is about the moduli space of matrix. So we're combining 2 worlds, which is our matrix, which are the objects, and we're talking about moduli space, which are guys from algebraic geometry. So we're combining these 2 pictures, but there's a certain friction. Algebraic geometry is based on rings, and matrices are combinatorial objects which don't really fit into the usual algebraic framework. So what we need are exotic algebraic structures, which form the base for both for generalization of matrices with coefficients in these algebraic structures, and a generalization for algebraic geometry, which extends to the combinatorial setting. And this was the plan of our original work when we set out to write this paper. And I was not so much convinced that there's much more to the story, but Matt said, you should do it. And I said, if I do it, you also do it. So I think. And at some point when we worked this out, to our surprise, we saw this really has applications to matrix theory. in the end. It's not just a nice geometric picture, but comes with applications. So this talk is somewhat structured as following. The first part, we look at this algebraic structures. Then I explain you what a matroid is. Most of you will know that, but I give you an angle on matroid theory, which is a little uncommon. If you don't know matroids, you will learn what a matroid is here from a certain perspective. Then I talk about algebraic geometry in this extended framework, so-called band schemes, what we use nowadays. And then the last part, I talk about how to apply this to matrix theory.
If we don't know what algebraic geometry is, we're going to learn.
You will learn what algebraic geometry is, yes. So I will explain you in 2 minutes what algebraic geometry is. So another way to think about this talk is the following theorem of Landmas learners. A matrix regular if and only if it's binary and oriented. That's a classical theorem, which is in this paper where it's introduced oriented matrix and has a 5 pages proof. It's not super difficult, but what I want to do is what in the first 2 parts, you could think of that I'm working towards introducing all of these concepts here. So at the end of part 2, you will be able to understand this statement, unless you do already. And at the end of part 4, I want to give you a 2-line proof of this theorem. Okay, let's get started. The first part is about this algebraic objects, where we use nowadays bands. In the original papers, we used ordered blueprints, but bands are kind of simpler and they do the same job. And this was later introduced in joint paper with Matt Bacon and Tom Jean. So here are some definitions. Right, there's a way. Okay, so just to set the ground, quantum monoid, this is a commutative monoid, so a semigroup A with a neutral element A and an extra element 0, which is absorbative. So 0 times A is 0 for all elements. It's just my language, the language that I want to use, pointed monoid, to refer briefly to these objects. A monoid, in particular point monoid, has a unit group, which are all invertible elements. Right? And then if we have a pointed monoid, we have an associated semiring, which are called the ambient semiring, which is basically, it's a semigroup semiring or monoid semiring, but I want to identify the 0 in A with the 0 of the semiring. So I'm just quotienting out by some equivalence relation if you want. But more explicitly, these are finite formal sums of elements in A that are not 0. So this is the ejection of A plus with these finite formal sums.
So 1.a is 1.a?
It's A, this is the
Great.
type of thank you. Yeah. 1 is neutral. Yeah. Strange. Okay. So, yeah.
Oh, just a little question. And are we insisting that 1 is not equal to 0? Like, are we allowed the 0?
We allow 1 to be equal to 0. Yeah. So we want to have a 0 object, which will be a terminal object in the category. That's allowed. In this case, it's now with this 1. And if we form this here, it would be the 0 semiring.
Do these little AIs have to be distinct? Or can they come with multiplicity?
They can come with multiplicity. So normally, if we form kind of a semi-group algebra, we want to have linear combinations, k-linear combinations. But since n-linear combinations, you can add up the same elements various times.
They are positive. They're all positive.
Yeah, all positive, not negative. Yeah. I can write A plus A. Okay.
But 0 is there, right?
There is 0. So you can add 0, but 0 is identified with an empty sum. So if I write A plus 0, it's the same as A.
So, but then on the right is like empty sum or?
Yes.
Okay.
This here?
absolutely on the right. So I can take the sum empty.
Yeah, the sum to be empty, this would be the neutral element, the additively neutral element of the summary.
Yeah.
Okay, here's one notion from Summer theory. An ideal of a Summer ring, particularly this Summer ring, just a subset. It's a sub-Summer module. So it's a subset that contains one, it's closed under addition, it's closed by multiplication by the Summer ring. Okay. So it was just setting the ground, and now comes the definition of a band. A band is a pointed monoid together with an ideal in the ambient Summer ring, B+, such that every element of V has a unique associated element minus A, such that A plus minus A is in this ideal. So let me tell you how to think about that. So we call this ideal the null set, and this minus A the additive inverse. So the null set are those elements, those finite formal sums that you think are equal to 0. Normally, if B plus would be a ring, you would say, okay, let's quotient out this ideal, and then our sum is really equal to 0 in the quotient. But the problem with Summer rings is that quotients don't behave so well. So if you have an arbitrary ideal and you divide by it, you might divide many more elements out. You have a categorical quotient, that's okay, but might be that your inverse image of 0 becomes larger than your original ideal. That's kind of undesirable for what we want to do, so we have to carry on this extra ideal, this extra quotation. It's a workaround. And this minus A should be thought as an additive inverse of A. Kind of additive inverse, but we cannot really form sums. Just have this notion of additive inverses. Particularly, there's an element -1, which is the additive inverse of 1. We will talk about signs in a moment. Okay. One more definition, and then I come to examples. A tract is something, so you should think of a band like a ring, and a tract is something like a field within the logic of bands. So this is simply a band such that the unit group is everything but 0. Particular 0 is different from 1. Okay, here's the example of a ring. If we have a ring, then the ring is naturally a band by defining the null set NB to be equal to all finite formal sums that really add up to 0 on the R. And if R happens to be a field, then the outcome is a tract.
So the first sigma happens in B plus. The second sigma happens in R itself.
Yeah, precisely. These are two different sigmas. This is a formal sum, and this is an actual sum. Okay.
What is idle in your paper, moduli space of method? Is it, can you explain first idle in terms of the band?
Yeah, tract is the same as an ideal. If you learn what's an ideal, it's the same as a tract in this talk. We try to kind of shrink down the terminology to something that's more understandable. So originally a tract is something more general. That's what I explained to you, and in former papers it's called an ideal. It's the same thing. But yeah.
Was this a band as an English word?
What do you mean?
What does it mean, and
the
why is it
meaning.
used here?
So there's like a band, something like circle, so there's circular meaning. The word ring in German, the original meaning means something like an association or group. So, no, sorry, I started around. So a band is something
You're thinking wedding band.
Yeah, sorry, a ring is something that goes around your finger, and band goes around your wrist or something. So this is one meaning, but the other one, so it's nice. You also know ring actually comes from this association and so on. And I mean, the music band is also cool. And we actually have fusion bands, so if you like jazz rock, loves the thing. Yeah, it's a little bit playing with words, but was kind of
So it's there
more
to
sketchy.
remind us about rings.
Yes,
And tract is like a tract of land, like a field.
precisely. We
Yes.
also have pastures that come up in a moment. And idyll was also connected to this association. So,
But we
Yeah.
take Oliver's thesaurus away.
Idiom is about English.
Oliver thinks it's English. Yeah. Please, if you're writing a paper with Oliver, do not let him name things.
that's ideas. Take minds off that. Okay, just let's see how our many characters fit inside. So F2 becomes a band. So the multiplicative structure I didn't explain. This is just the obvious thing. There's nothing to think about. But the additive structures now, well, we just take the idea which are all multiples of 1, where n is even. So whenever this becomes 0, it's an example of F2 is a field, so we just apply this mechanism. Now, more interesting are these other guys, Krasner hyperfield. Well, if you look at it, we want to know when we add up 1 n times by itself, can the outcome be 0? And if we add 1 plus 1, it's 0 or 1. If we add plus 1 again, then we would apply plus 1 to 0 and to 1. And the outcome is, again, everything. So once we added up 1 twice, and we add up more ones, it stays 0. So it's the nodes that are all multiples of 1 except for n equal to 1, which is not in there. For the sign hyperfield, we have to think about formal sums of positive reals and negative reals. And when can sum be equal to 0? Can only be 0 if either the sum is completely empty or if there's a positive and a negative real appearing. And that's this outcome here.
So for the Krasner hyperfield, when you view it as a pointed monoid, you view it as a pointed monoid with multiplication. Yes?
Yes.
And then you construct this semi-ring, ring algebra with entries in N. But now you are defining an ideal in this ring algebra, which doesn't know the addition K.
Yeah.
In terms of addition, all of a sudden.
Yeah, we're replacing the addition of the ring by this node set.
By the
But the node set remembers the addition. You can reconstruct the additions from the node set by, just take A. If you wonder what A plus B is, then you will find an element A plus B minus C in the node set. See if precisely A plus B. Yeah.
But in the cross, in the
Can you say again, why is that the right NK for the Krasner hyperfield? Or sorry, in what sense is that the right?
A way, if you know what a hyperfield is, then you would take the same recipe, but you say 0 is in the hypersum of these elements. But I just give you a definition for this one object here.
But why?
So you're saying you can recover the hyperfield from this?
Yeah, I can recover the hyperfield. So there's maybe just since we're at this topic, I prepared a second slide. Since there's so many names around, just glance at this. I don't want to explain this completely, but want to explain you a little bit the landscape of where objects lie. So we have fields and rings, which are classical objects. And then there are generalizations of fields, which are hyperfields and hyperrings of rings, which are well studied. I think papers go into thousands, but at some point they became important because of VRO introduced hyperfields into the tropical setting. Don't want to say too much. There are partial fields which appear in Matroid theory, also fuzzy rings which appear in Matroid theory, and all of the structures are example of tracts or bands. So these arrows means we have fully faithful embeddings of categories. In a natural sense, so very natural functors. You have to work a little bit. And just to explain a little bit, I don't want to really dwell on that, take this as a definition for now, but I want to explain that this name is hyperfields and here partial field, they really come from these embeddings of subcategories. So there's a description, and for hyperfields, precisely what I said before. We take this recipe, let's say the arrow is in the hypersum element.
So should I work out this as you're saying, you have a recipe that given a hyperfield gives me a band, and if you do that recipe to the Krasner hyperfield, this is what we get.
Yeah, precisely.
And the same thing for.
But for this talk, just take it as a definition.
Can I ask a question?
Yes.
For example, in this Krasner hyperfield, right? So if you add 1 + 1, you get 0, 1. But what happens if I add 0, 1 + 0, 1?
As a subset.
It doesn't seem close, this operation plus. What does it happen?
Yeah, you take unions over all sums of combinations.
So then do I get 0 and 1 with multiplicity too?
No, the hyperfield forgets about multiplicities. This guy here it's still visible. So multiplicity. So in some sense, the band knows more.
I'm trying to make sense of the fact that all these tables are finite tables, but it seems that here you're in principle working with infinite objects, right? This is additive. So B plus is an infinite object, and then nobody says that if you introduce this ideal that you should collapse to some finite table. So
yeah, you cannot collapse the ideal. If you
can't even collapse.
If you collapse this as summering, you get to zero summering. This is an example where it's really badly behaved.
So how do you see that you get only finite tables when? Does the question make sense? I don't know if I phrased it clearly. I have not reconciling these two things.
Yeah, it's a change of perspective. So here we really have multi-valued operations. And I avoid this operation by saying we have this ideal are replaced by some other type of information. And this really changed the perspective, changed the language, changed the category. So these are kind of poorly behaved categories. Partial fields.
And I rephrase this question a little bit. So since plus is not an internal operation, it's not, because 1 + 1 is not. What do you get if you do parenthesis 1 + 1, close parenthesis, plus parenthesis 1 + 1, close parenthesis?
You would perform these things. I mean, first of all, you identify one with a singleton one, and then you have operations on sets.
Yeah.
Subset plus subset means the union over all pairwise combinations. And then you perform it according to the parentheses. But for the Krasner hyperfield, it turns out that it doesn't matter how you put the parentheses. For other hyperfields, it matters.
That's because you forget about the multiplicity. But here you have the multiplicity.
Yeah.
B plus, it seems that you have many more points in this object than you had in the original object you started with.
You should think about the monoid as, I mean, the elements of the monoid as really the elements, which is finite. So the semmering is big, but it's an auxiliary object, which is in background.
Yeah.
Yes.
So is it possible to see from this N whether it comes from a hyperfield?
It is possible to characterize hyperfields within bands, but the characterization is ugly. Particular associativity for addition here, which is already complicated in the language of hyperfields, will be something very unnatural in this language.
And then giving N or giving a table, this is equivalent information.
Yes. Yeah. In other words, I mean, this embedding over there is fully faithful. That means you can recover the information. Yeah. Okay. Last guy is a regular partial field. Here's a node set is just we add up 1 as often as -1 to get down to 0. Similarly, like the single case. Okay, I talked about fully faithful embedding, so let me briefly tell you what are morphisms of bands. These are simply structure preserving maps. So it preserves the multiplication of the monoids, preserves the constants. And whenever we have a sum in MB, then applying F to each term of the sum lands in the node set. So most natural thing that you come up with, and that defines as a category of bands. And here are two examples. One that's just what we would like. The map from R to the sign hyperfield becomes a morphism in this language. And then this, three examples actually. Then for every band, there's unique morphism from the regular partial field into B. By just, we're mapping 0 to 0, 1 to 1, and -1 to the -1, to the additive inverse of 1. And well, these are the minimal relations on the addition table that you could come up with. So that's why there's this unique morphism. In other words, this is an initial object in the category of bands. And similarly, we have a terminal object for tracts. This is more interesting, which is a Krasner hyperfield. And so for every tract F, there's a unique map to K that maps every non-zero element to 1.
So start with the semi-ring, and the summations form are always the negative stars. How do you know there is a negative of 1?
This is one of the axioms of bands. So,
oh, okay.
Yeah, for every A, there's -A. Yep. So -1 could be equal to 1 in particular, which is the case for these two guys here. Okay.
So if I replace the word tract by band in number 3, it's not true.
No, then the terminal object would be the 0 band that we had before. It's like, for rings, the terminal objects, the 0 ring fields don't have a terminal object, but here we do. Right. Okay. And this is a map that's important. That's why I gave it the name and called it the terminal map. Will come up. Okay, now I have to probably.
Why does polyfaithfulness imply that you can actually recover the whole multiplication for the hyperfield?
What fully faithful means.
What does it mean? But where's the Hob? Where's the Hob's going to be the
If you
actual?
think about going from rings to affine schemes, you can get the ring back in the end. It's an object of a different nature, but it has the same information in it.
The categories. I can explain this later with count. Let me continue for now. So I want to introduce you what's a matrix. And introduce you actually matrix with coefficients and bands, but to get you on the same boat, let's start with the field. Everybody knows fields, so we don't have these exotic objects anymore. We fixed the rank R and N, which is the cardinality of the ground set, which are fixed to be 1 to N, and a field small k. So K matrix is something that you also all know. On E of rank R is simply an R-dimensional subspace of K to the N, nothing else. So we're doing linear algebra. Okay, in matrix theory, there are cryptomorphisms. So we have a lot of different ways to speak about a matrix and characterize in different forms. Here's one that you probably also all know. The R-dimensional linear subspace of K to the N, it's the same as the K-rational point of the Grassmannian. It's cryptomorphism means it's an equivalent characterization of the same thing, but not obviously equivalent. So the Grassmannian GRN of K, we consider this as a subset of the projective space P capital N of K, where capital N is N choose R minus 1, given by taking Plücker coordinates. Right? So now I want to generalize this definition to other bands. And I'm claiming that this geometric perspective is really the right perspective to take. But now think about, we know what Grassmannians are over fields, but over bands, this is maybe not clear to everybody. So let's think about, take a step back and think about how would we explain what's a K-rational point of a Grassmannian to an undergrad student who has never seen algebraic geometry. Here's a way to do that. So a K-matrix or a K-rational point of the Grassmannian. This is a K-star class of something that's called a Grassmann-Plücker function. In matrix theory, geometers would call it a Plücker vector, which is a function from E choose R, the indexed set, so R subsets of our ground set E, into the field, such that, well, one of these coordinates is non-zero, it's a unit. And the Plücker relations are satisfied. So there's this quadratic relations and the coordinates. And I don't read this out. You know them and you don't need to read it, otherwise I think it's no meaning of drilling into it, but these are the relations that really carve out the moduli space of R-dimensional subspaces and K. Okay, if we now want to do a band, did you notice what happened? Let me go back. So you have two pictures and you have to find 5 mistakes in the second picture. So pay attention what's happening. Oh, wrong direction. So did you notice the 5 mistakes?
You've been.
I love about it. Okay, so I mean, I'm taking now a band and you just fill in, instead of K, you place it by B, and this all makes sense. But this is just a definition. B star is a unit group, so we can kind of, B star class means multiplying all values with B star. This is set, this makes sense, this makes sense. The only thing where it's kind of something normal happens is equal to 0 is replaced by being an element of the null set. Because in a band, we cannot really form the sums, but we can talk about formal sums of elements, and we can evaluate if it's a term in space. Think about the sum being equal to 0. So the logical thing to do.
But I thought there's minus signs there. I thought you only had positive signs in your end.
No, it's built in the definition, the existence of minuses.
Oh, minus.
Yeah, for every A there's a minus 8, and for 1 there's a minus 1. So
Is that associative, or does that mean the minus of the first one of those? Is that minus of this times this, or this times?
So that minus has to be taken in the band, I guess, not in
yeah,
the.
you could say -1 is a structure constant of the band. Similarly, like if you have a group, you could say the unit element is structure constant, or you just say the existing such that. But if you want, -1 is just a constant in your band.
I think Diana's asking if minus A times B is the same as minus A times B.
Yeah, minus A is -1 times A, so everything's.
Yeah, so there are 2 important basic facts. Gibt es here. -1 is the axioms tell you that -1 squared is 1, and that -1 is -1 times A. So this follows from the axioms.
So I think so what you mean by DX class? Like there are two of them are the same, like 2 functions.
This is if you have the diagonal action of that, you multiply all values here by the same element. It's like homogeneous coordinates.
B comes from a ring. It's the same thing as an R, a ring R, is the R value point of the Grassmannian.
No, that's subtle. I explain this later to you. I mean, it was a matter of time, not from that. Okay.
But could just say, because in a ring, -1 would have 2 meanings. I guess, is that the issue? The ring would you something?
No, it's let me not go into that because this will cost me 5 minutes. Okay. So a matrix now, yes, a matrix is just a K matrix according to that definition. Everybody who knows what a matrix is will think it's horrible to define it that way. But maybe if you didn't see a matrix, you appreciate that it's something like a linear subspace for the Krasner algebra. So it gives you some intuition as young as nodding. So, and it makes a point for this talk because I want to dwell on this characterization of matrix.
But we should think about it more like as a representation of a matroid than a matroid.
Yes, but if you think about it like this, there's a unique, for every matrix, there's a unique K representation. So you can identify that. It's, if exercise for everybody knows matrix, this here encodes exactly the strong basis exchange axiom for a matrix. If you take null set of the Krasner hyperfield. Good. Here's an example of a source of matrix, for those who don't know that. If we have a field and we take a k-rational point in the Grassmannian, which I write as this function represents an index set, the Plücker coordinate. And if we take the terminal map Tk, which maps every non-zero element of field k to the Krasner hyperfield, to 1 in the Krasner hyperfield, then the composition of delta with this map Tk is a matrix. And this is so-called representable. It's representable over K. It's precisely the notion of being representable. We can turn this around and say, well, if we have any tract F with terminal map Tf, then a matrix M is representable over F if there exists a Grassmann-Plücker function over F, so an F matrix, such that M is composition of delta with Tf. Or again, the notion of being representable over any tract, not only over fields. Over fields, it happens to be the same thing as the usual notion, but we can also talk about representation over other tracts.
Okay, so you can talk about integral models.
You could, yeah. I don't.
No, I don't want to get into it, but can we talk about that?
Yeah, the notion provides a notion of
Flexibility.
Yeah. I'm not sure precisely what it is. It's closely connected to the regular partial field, which will play a role in a moment, but will be a bit different.
In your definition of matrix, were you requiring it to have at least one basis?
Yes, this is.
Okay.
K is a tract, right? K
Yes.
is a tract.
Yeah.
So you've defined this notion for arbitrary bands, but you only use it so far for tracts.
Yeah, we come to just in a second to general bands. This is, I mean, this theory was developed by Baker and Bowler for tracts, and there you have good cryptomorphisms. But if you want to geometrize this, I mean, if you do algebraic geometries, fields are not enough. You need rings. That's why we need bands here. Okay. So here are some further definitions. So if we have a matrix M, we call it regular if it's representable over the regular partial field. That's equivalent to the usual notion of regular. Matrix is called binary if it's representable over the finite field F2. And as I said before, this is equivalent to the notion of being representable over the field F2. Sense. Orientable corresponds to being representable over the sign hyperfield. Here we are leaving this domain of fields. And it just comes down to the usual notion of being orientable. And now you see the sentence makes sense. A matrix is regular if and only if it is binary and orientable.
The bullet points are theorems, aren't they?
This, for users are definitions. For other people who know what it is, these are theorems.
This for the previous, to the theorem book in 78, see them as theorems.
Yeah, these are actually, there are other definitions and they are equivalent, so they're theorems, yeah. But they're not very hard theorems. This here is a medium hard theorem, I would say.
Yeah.
Okay. Okay, that's the part about matrix. Let's do more geometry modular spaces. So now my promise 2 minutes where I define you what a band scheme is. So let's start with just thinking about what is a scheme. So a scheme, you all learned Hartshorn and it's something complicated. But actually, if you work with a scheme, most of the times what you're interested in is one essential invariant. Or it's a class of invariants, which are rational point sets. Working often with rational point sets. You have complex scheme. We work with the C points of the scheme with the variety. So the Uniter lemma tells us the scheme is actually determined by what it does as functor of points on all algebras over this field. So equivalently, we can say a scheme is a functor. So we do this for band schemes. Cheating my way out here. I won't give you a complete definition, but what's important. So an affine band scheme is nothing else than a representable functor from bands to sets. Representable means it's of the form hom b, comma, applied to whatever band. So B is the band that represents our functor. A band scheme is a functor, let's call it X, from bands to sets that has an open cover by affine band scheme. And I will not explain you what this open cover by affine band scheme means, but instead I will give you examples that we work with, and I hope you trust me that are really band schemes. This definition, just a side remark, this is not very horrible. It's relatively painless to say, but you need to work with sheaves on certain Grothendieck topology for affine band schemes, and then you take columns of certain diagrams, but I don't want to get into that. Morphism of band schemes is simply morphism of functors, also very simple. So now you all know hopefully what a band scheme is. Or so the first example of a non-affine scheme that you think of is projective space, and this is as an avatar in the language of band schemes. So this is a functor that takes a band B to the set of all n+1 tuples of elements in B, for which one of these coordinates is a unit. And we divide out by the diagonal action of B star. Matt, I'll explain this later too.
Is a normal scheme a band scheme?
No. You need extra choices to make this work. Okay, and then the most interesting example for this talk are Grassmannians. So the Grassmannian Rn is a functor from bands to sets that sends a band to the set of all homogeneous coordinates. So, I mean, it's a subset of P to the n choose R minus 1. Tuples like this, model, diagonal scaling, such that the Plücker relations are satisfied by this delta. So it's really, you see from this already, it's the same as the B matrix. It's a B star class. We have this B star class of Grassmann-Plücker function. And this was an insight which got this whole project with Matt started. He had this paper on matrix with values and tracts, and I saw a tract is an ordered blueprint. Nowadays I would say a band, so ordered blueprint is somewhere on this blackboard. And his notion of a B matrix corresponds to a B rational point of the Grassmannian. And well, when we observed that, we said, okay, we want to make properly sense of that in algebraic geometry manner. So this just talks about rational point sets, but the Grassmannian really should be a modular space in the appropriate sense. And I keep this short now because I want to get back to the proof of Lorentzian's theorem.
Oh, projective space is no longer a special case of Grassmannian.
It is.
When R is n-1?
I guess so, or 1.
I'm less.
Equal to 1, right? You want singletons. Want your ground set E to be 0 to n in this case. Then you want to take singletons in here.
Okay.
So this index set, sorry. That you have to do. I mean, you have a canonical isomorphism between GRN and G. Doesn't matter. Okay. So just let me tell you, to make sense of moduli space, we have to talk about universal family on the Grassmannian. So we don't talk about matrix over bands, but matrix over geometric objects. And this is what we call matrix bundles. I will not define for you what a matrix bundle is because it needs its open coverings, which I didn't define before, but give you a taste. So this is an isomorphism class of Grassmann-Plücker function, which is now a function from E choose R into the global sections of this line bundle, which is a band. So we have function into a band, as relations, where L is a line bundle on X. So if you write out all this definition, you arrive at a definition of a matrix bundle. There's nothing hard about that. I use this. And then our main theorem says, first of all, just a sanity check for every band B, and the affine schema represented by B. The matrix bundles on X correspond canonically to the B matrix. So this notion of matrix bundles really extends the notion of B matrix to a geometric setting. It's the same thing. And then the main part here is that for every band scheme, there's canonical bijection between homomorphisms from X into the Grassmannian and matrix bundles on X of rank R on the ground set 1 to N. And this says, in other words, the Grassmannian is a fine modular space of matrix bundles of this given rank in the ground set.
The global sections of L is a band?
Yes, this has naturally a band structure. Yes.
Is there some notion of like a vector bundle or like churn classes that we can have over these band schemes?
Vector bundle, yes. So the matrix bundle is the same as a vector bundle in a certain sense. So matrices have vectors associated, so you do a cryptomorphism. Churn classes, that's our topic. So this would be nice to develop, but I don't understand yet. Just to conclude here, this story of the modular space. There's a universal family, so a universal matrix bundle on the Grassmannian, which is, I mean, it's the usual story of modular space. You take the identity morphism, and this gives us a matrix bundle on the other side. And then the same way, if we take, I mean, every matrix bundle is a pullback of this universal bundle. I mean, this just follows from abstract nonsense, but it's this usual thing. If you have a fine modular space, you have a universal family, and every other family is a pullback from this universal family. So this works neatly in this context. So it's quite satisfactory from this algebraic geometry. Let me now go, to probably speed up a little bit, into the applications, foundations of matrix. First thing is, we turn this bijection from theorem part 2 around. So every k rational point of the Grassmannian corresponds to a matrix. So if we turn it around, given a matrix, this defines as a k rational point here. So a k rational point means it's a morphism from the Rothier spectrum of k, it's this hom k slash, it's a band scheme, to the Grassmannian. Since k is field-like object, this here behaves like a point and it has an image point. So I didn't tell you that, but it's like that. If you work it out, and this image point, xm, this has a residue field, which is really a tract. Or here fm, sorry, this should be a. Okay, this. There will be later in different FM. I hope you don't get confused, but this residue field is what we call the universal tract. So if a matrix, this matrix determines the point in the Grassmannian, and this point has something like a residue field, which is really a residue tract. And this residue tract governs the representation theory of the matrix. So first application is the following. Can consider Singh-Schubert cells. So Singh-Schubert cell of Grassmannian is a locus where you have a prescribed pattern of vanishing Plucker coordinates and you take all points that have this pattern. So in other words, we take a matrix, which is this pattern of zeros, and we define x sub m of k to be all Plucker vectors such that the composition with the terminal map is this given matrix. It just means the Plucker coordinate vanishes if and only if we have a non-basis of the matrix. Then we have the universality theorem, which took many shapes, and there are certain names attached to it, which basically says that since Schubert cells can be arbitrarily complicated. And
can you summarize what are the differences between the different names a little bit?
so Neff proved this originally for oriented matrices and representations of as real. Sturmfeld's names in the book that he proved at the same time independently, and not totally sure. I think he does it for all fields or not. I'm not totally sure. Sorry. Laforgue proved this over the integers.
Which Laforgue is this? Which Laforgue is this? Which Laforgue?
The field level. And Bakil used the statement to give this a concise meaning by saying that all kinds of singularities can occur. Neff at Schoenfeld's Laforgue talked about certain equivalence between schemes, and every equivalence class is hit by the Singh-Schubert cell.
And by complicated, they mean different things. The meaning of the word complicated is different for different people.
It's different for different people. Don't want to have a concise statement here. I just want to say that this gets out of hand. Grassmannians are very nice varieties, but if you take the Singh-Schubert cells, parts of the Grassmannians, these are arbitrarily complicated varieties. You get close to every isomorphism type, up to taking open subsets of triple vector bundles. Okay, here is a statement. We take the universal tract, so it should be Tm, as typo before. Then there exists a canonical projection of this Singh-Schubert cell with the homomorphism space from the universal tract into K. Or the universal tract knows about this Singh-Schubert cells. That's all the information in there. Which is nice to have the theorem, but it's also bad news, which means this universal tract can be as complicated as possible, and it's maybe not so useful.
But if K is a ring, this won't be true.
Sorry?
If K is a ring, this won't be true.
No, I don't think so. Yeah, to think about that, probably not. And corollary of that is, well, M is representable over K, if and only if there's a morphism from Tm to K. But again, Tm probably is very complicated and not so useful.
You just put a definition of TM. Okay.
Sorry.
Residue tract, I think.
It's a residue tract.
Could you just go back 3 slides or 2 slides or whatever it was?
Yeah, this is a type, it's Tm. So we take a matrix, the corresponding points of Grassmannians, this has a residue field with a universal tract. Residue field means it's a tract. Just.
He didn't tell us.
Okay.
Yeah.
I see. So we're not being.
I don't give you an explicit definition of that. I just want to appeal to your
Next
intuition.
slide has the definition.
What was the next slide then?
That functor. It's something that represents that functor.
Yeah, if you want, this is a definition.
It's a definition.
So you can write it down very explicitly by taking Plucker coordinates and endowing all Plucker. This gives you, it's very explicit, but it doesn't tell you much. So I skip that here. Want to get to a point in my last 5 minutes? So I've
in this theorem, K could be arbitrary tract, right?
Yes.
I thought you said it's not true if K is a ring.
Yeah, it's not true for bands. It's true for all tracts.
Yeah, I mean, there's a discrepancy by taking rational points in bands and rings, which is different. So I have to think about it. Otherwise, in the logic of bands, let's do this. Let me explain you one last twist and get back to Los Vernes. So there's an important observation. Universal tract is complicated, but we can simplify it because many tracts have the following property. If we take a map from E choose R to F, where F is a tract, and we fix a matrix that represents the zero pattern of this function, then this function is a Grassmann-Plucker function or a point in the Grassmannian if and only if it satisfies the three-term Plucker relations. So it doesn't need to satisfy all Plucker relations. This is not true if we don't ask that M is a matroid, but if we know, we start with a matroid and we ask for representations, and for many good tracts, this is true. Let's say good tracts, for this talk, we call them perfect tracts. It's really a different definition which implies this property, but let's not go into that. And examples of perfect tracts are all for protagonists, which is, yeah, it's not totally easy to prove, but they're perfect. So this means if we look at representation, we only need to check three-term relations in the null set. So there's an A minus B plus C, just three additive terms. So which leads to definition of this guy here. Pastures. Sorry, I covered parts of that. So pastures are just tracts which are determined by the three-term relations. So either you say the null set's generated by three-term relations, or we just truncate at three terms. Like June introduced pastures in his lectures. If you and then the universal pastures like the three-term truncation of the universal tract. So we are simplifying the relations to just check three-term Plucker relations. And then there's one more thing that we can do. Namely, we can look at the subpasture, which is called the foundation, which is generated by cross ratios, which are expressions like this. We're taking, sorry for going back. We're taking two terms of the Plucker relations and we divide them. So we take the ratio of two of these terms, which is something like this here. And we take the sub-monoid generated by this and all null relations that are based on this. If you look at that, you see that every element appears with the same multiplicity in the numerator as in the denominator. So these are kind of multi-degree zero elements in the coordinate band, if you want.
That's not a residue field. That's not a residue.
No, it's not a residue field. It's kind of, we are simplifying things. So first of all, the first simplification is only take three-term relations. The second one is, well, we can go down to a subpasture, which is smaller. And this guy now is very computable, and we can use it to determine representations. And this is what I want to show you on the last slide. So the first observation is that this guy still can tell whether a matrix is representable or not over perfect tracts because of this fact that I told you before. So a matrix M with foundation Fm is representable over a perfect tract F if and only if there's morphism from Fm to F. And this now is much more tractable using the tract or the usage of language here. Yes.
Why go to the foundation instead of working with the universal tract? Is because the universal tract is too big?
Yeah, so the universal tract has all Plucker relations. This is horribly complicated, which is reflected by Neff's universality theorem. Universal pasture is simpler, but it has a lot of free variables, so things just blow up. The foundation is much smaller, and let me give you one example where it just turns out very beautifully. For the class of regular matrix, this is characterized by the foundation being equal to the regular partial field. Super clean statement, which hopefully convinces that the foundation kind of captures some essence of the matrix in a very clear way. For binary, we have similar characterization, matrix binary if and only if the foundation is either the partial regular partial field, or if it's F2. So it's very simple. By the way, the statements here, this is all simple to prove. These are not deep proofs here. Tomorrow I will tell you some deeper things.
Well, every regular matroid is binary. Is this a trivial fact?
Yeah, I mean, the original, there are two definitions, and I don't know which is the original definition. One is matrix represented by unimodular matrix, which is close to being representable over F1 plus minus. The other one is representable over every field. So from the second definition, it's trivial, right? Okay, let me get to the grand conclusion of this talk. Matrix regular if and only if it's binary and orientable, and we can prove this from a statement in this slide. So it's binary and orientable if and only if it's using this thing here, if and only if it's the foundation is F1 plus minus or F2, and it's orientable. But orientable means that there's a morphism from the foundation into S, the sign hyperfield. But there's no morphism from F2 into S. It's something that you can check, exercise for you. So this means the foundation is F1 plus minus. Using this statement, we conclude this M is regular. Okay, so this is the conclusion of this talk. Just let me say something for tomorrow. We'll give 2 lectures which exploits these 2 aspects of this talk. The first one talks about foundation applications to matrix. So I really want to show you how to show more interesting results with this technique. The second one, completely independent, goes into the geometry, and I want to tell you how this moduli spaces give a natural solution to Pitt's theorem about buildings and algebraic groups over F1. Okay, that's it.
Questions?
Is the moduli space a scheme of some kind? I mean, what is it?
It's a band scheme.
A band scheme.
Yeah.
Can you talk regularity? Can you talk?
No, this is, I don't know. I didn't think exactly about regularity, but I think this is also hard to characterize because you really need modules. So we don't have, I mean, something that you can carry on algebraic geometry to a far point, but something that breaks down completely is we don't have abelian categories anymore. So everything that's based on abelian categories becomes impossibly hard. Not impossibly, there's some workarounds, but you have to work a lot to establish things based on that.
What do I need to turn a scheme over a ring into a scheme over a band?
You need to choose something like coordinates. So this can be in different ways. For example, if the easiest way is you embed it into a toric variety, and this embedding gives you everything that you need turned into a band scheme. Another way of seeing is you need a covering by affines, and this affines you can spectrums of rings which can realize as bands. Then you can do them back together. I mean, needs covering and then coverings of the intersection. It's something like a gluing datum.
And the result is independent of the.
It's not independent of the traces.
It is dependent.
Yes.
It's closer to a log scheme than a scheme.
Yeah, a log structure would also give you a band scheme, except for technical caveats. So sometimes you get something stacky then.
Can I ask, I mean, so there was an original proof of this theorem, which was presumably purely combinatorial, right?
It is.
And now you have a 2-line proof that relies on a whole bunch of formalism and several non-trivial theorems. So I wonder if you now unwind what you have, what these 2 lines actually mean. Have you given a kind of geometric interpretation of the original combinatorial proof, or have you discovered a completely new way of accessing this kind of information?
I meant to look this up precisely because I was wondering about that. I'm not totally sure. I mean, the combinatorial proof is about 5 pages. That's as far as I got. And I wanted to look it up yesterday evening. I'm not totally sure. I mean, it's not such a hard proof, so you can go from one to the other without too much work. But I think it's, yeah. Answers, I don't know. I mean, tomorrow morning I can tell you more precisely with other statements, how to see this from classical point of view and the modern point of view. With this, it's simpler, but I don't know precisely the comparison because I didn't read up on it.
But in this more general setting, in these other situations, is the general feeling like this is giving you a more understandable interpretation of the kind of magical proofs that people do in combinatorics?
Yeah, so in this other situation, the foundation really extracts the essence of something in a certain way. So the one driving thing behind this more complicated thing, not this here, is taxonomy theorem, which goes into many proofs about matrices, which also goes into structure theorem of foundations that I explain to you tomorrow. But it's somehow the foundation really takes out the information in a very effective way, but it's the same kind of machine that's driving this proofs. Yes.
So how hard is the middle one here? Characterization of regular and binary.
This is each page, so it's not very hard.
So besides ordinary matrix and orientable matrix, do you get other interesting classes or extensions of matrix through tracts? Like, can you say the word Matroid, for instance, or like?
Matroid, it's I don't know. Yeah, it's something worth to figure out, but evaluate matrices are matrices of a tropical hyperfield. Something like phase matrices, which are matrices of a phase hyperfield. You have something, a very interesting connection between Lorentzian polynomials and matrices over so-called triangular hyperfields, which are almost the same. Topologically, they're the same.
Can you say things like flag matrix or Coxeter matrix?
Yeah, that's kind of an story, unintended. You need different types of Plucker relations for that. So something, this is worked out by Tong and Dong Yu for even that in the even data matrix in the Lorentzian case, then you take big relations. Also get there. And in general, it's something that I would like to do, but it's a bigger box that you open. It's not on.
So in some sense, you're taking the Grassmannian and you're using Plucker coordinates to embed it, and then you're pulling back the log structure. And then that's the.
Can you repeat that?
So the Plucker embedding gives one way of putting the Grassmannian into projective space.
Yeah.
And then projective space has a log structure as the toric variety. And it's that log structure that's somehow giving the local coordinates on.
Yeah.
And so for these other spaces, you choose your favorite embedding in projective space through LV boss or however you wish. And
yeah, so are we talking about Coxeter matrix?
Yeah, I'm also wondering about the context. Yeah.
One attempt that has been made was that look at the fundamental weights of the group and then look at the representation. And there are some theories that gives you like a canonical basis of these representations. And this is supposed to be the indexing sets of the potential basis of the Coxeter matrix. And potentially, like hypothetically, you can write down the defining relations of the corresponding Grassmannians in this pool. And they should tell you something and combinatorial, say over Krasner hyperfield or something.
But the coefficients, like if there's a 2 in the coefficients of the equations.
That's right. Yeah.
So you simplified the universal tract to this foundation. If there's still some finesse thing, like saying that these foundations can still be arbitrarily complicated.
While you're talking, can you put the foundation slide back up?
I think in a sense, yes, but not totally sure. Which slide do you want, Ryan?
Foundation. Is this, should I think of it as like your objective realization?
It's
A quotient by the.
It's a realization space, so you quotient out the terms.
Yeah, projective, yeah, exactly, so that would have, the answer would have to be yes then.
Yeah.
So if I have a point in the Grassmannian, there's also like a dual Grassmannian, which comes with Booker relations. If I have a B matroid, can I define its dual easily?
Yeah, you can define a dual, and so this is paper of Baker and Bowler, where they define duals of B matrix, minors, and cryptomorphisms with circuits and dual pairs, cardinal signatures of circuits and co-circuits. And so they work out all this formalism. This is reflected here by geometric construction. So the dual is there's a canonical morphism of the Grassmannian Rn with the Grassmannian n minus Rn, like in usual algebraic geometry. And the minors are also captured by maps between Grassmannians. So from Grassmannian, you can take a locus where certain variables vanish and where they don't vanish. As they don't vanish, you can probably exclude this element and go to this Grassmannian, and on the other locus can contract it and you go to a smaller Grassmannian, something like that.
One more question. Yeah, go ahead.
Is universal pattern is foundation or universal pasture?
Good.
Universal compatibility between the universal partial field and foundation. I just confused.
Universal partial field, when it exists, is a universal pasture.
What's a universal partial field?
He knows.
So,
from Penderving
Yeah.
transform, yeah, of course, sorry. So if the foundation turns out to be a partial field, it's equal to the universal partial field. But in generally, there's the universal partial field is a quotient of the foundation. There's a quotient constructor, so from the foundation you get automatically, you can recover the universal partial field, but normally the partial has more information.
What did you?
Okay, we'll continue tomorrow.